Welcome back to the video series on integration and differential equations. In today's video, we're going to look at integration by parts. And there are two main methods for doing integration by parts problems. There's the tabular method, also known as the table method, and there's the formal method. In our previous video, we looked at the tabular method, and today we're going to focus on the formal method. Here's the key formula we're going to be using. The integral of u dv is equal to uv minus the integral of v du. So in terms of notation, very common to write this formula in terms of u and v. So I just try to make sure that I can really tell the difference between my u and my v. The v, for example, has a long horizontal tail on it, so you can tell it apart from the u. So we'll make sense of this formula as we go through an example. Let's evaluate the integral of arctan x with respect to x. So first thing we want to do for integration by parts is we want to break the integrand into two different factors. And all we see here in the integrand is arctan x. But really, we could think of that as 1 times arctan x, and that suggests how to get our two factors. So one of the factors will just be 1, the other one will be the arctan x. So let's say we wanted to try the tabular method that we saw in the previous video. So we'd set up a column for what's going to be differentiated, what's going to be integrated. So our first instinct might be to say put 1 in the D column, arctan x in the integration column. And the problem with that is that we do not know a formula for the integral of arctan x. In fact, that's the whole point of the problem. We're trying to integrate arctan x. So if we knew how to integrate it, we wouldn't need to do this approach in the first place. So we have this big question mark here. That means we're not going to be able to complete the table, and let's say this version of the tabular method doesn't work. All right, so that might be our first thought. Second thought might be, hey, let's try the tabular method the other way around. So we'll set up our differentiate column, we'll set up our integrate column. This time, let's let arctan x be the thing that we differentiate, and 1 can be the thing that we integrate. Okay, so let's try that. Derivative of arctan x, that's going to give us 1 over 1 plus x squared. And the issue with this is that we could keep taking derivatives here, and the derivatives are going to get a little bit messy as we go through the different steps here. But we're never going to reach derivative equals 0. So no matter how many derivatives we take here, we will never reach derivative equals 0, and so again, the tabular method doesn't work. Let's summarize our discussion at this point by saying the tabular method doesn't work no matter how we set up the table, and so we're going to shift instead to the formal method. So in order to apply the formal method, we need 2 rows of the table. So we're going to set up the table the way that we did in the last situation. If we put arctan x in the D column, then we are able to find the derivative of that function. And that would put 1 in the integration column, and that's great because we know how to integrate 1. So that would integrate to give us x. All right, so we've set up the table with 2 different rows here. Now what we're going to do is label the quantities in the table. We want to label them as u and dv, and you can see that we're setting up to use this formula. So u is going to represent the quantity that's being differentiated. and dv will represent the quantity that's being integrated. So let's go up to our table here and let's label these 4 different functions. So the quantity that's being differentiated, that's arctan x, we're going to call that u, and its derivative, we're going to call that du. The quantity that's being integrated, we're going to call that dv. So in this problem, 1 is acting as the dv, and whatever its integral is, we're going to label that v. Now I want to point out there is a slight abuse of notation that's happening here, because if you look at the, say, bottom left-hand corner here, we're calling this du, and yet we're not actually seeing a differential in here. So if we were being absolutely correct with the notation, we should say du is equal to 1 over 1 plus x squared times dx. But typically, just for the sake of keeping things organized in the table, we usually don't write that. So we are abusing notation, but we'll see that when we get to the end of the problem, we are using all the notation correctly. So by the end of the problem, we'll have sorted out all these wrinkles here. All right, so let's think about applying our formula. I'm going to copy the formula down so that we can plug into it. We've got the integral of u dv, and that's going to equal u times v minus the integral of v du. And we've got our 4 quantities labeled, so let's try plugging in here. Okay, looking at u dv, so we'd be multiplying these 2 quantities together. In fact, we're just multiplying the 1 times the arctan. So 1 times arctan x would give us arctan x. And now I want to be careful about the notation. So since we're writing an integral, let's throw a dx on the end there. So left side, we're saying the integral of arctan x with respect to x is equal to, okay, now we're going to multiply u times v. So that's arctan x times x. That would sound better if we write x arctan x. So we'll write it that way. And then we'll subtract off the integral of v du. Okay, so multiplying v and du together, we're just getting a fraction, x over 1 plus x squared. And again, with this discussion about the notation, remember in the table, technically we're being a little loose with the notation here. We don't have a dx in here, but when we write down the integral, let's try to observe the notation correctly. So we want to put a dx on the end there. Great, so what we've got now is a formula for figuring out the integral of arctan x. So yes, the right side does look a little bit more complicated, but what has happened here is we've turned our original integral, this integral here, which we could not compute directly, we've now turned it into an expression and another integral which we will be able to compute. So we will be able to evaluate this second integral here, and that will lead us to our answer. So to recap where we're at, we set up the table, we labeled the table, and then we applied the formula, and this is where we're at so far. We've got this big expression here. So let's work on the right side here. What we'd like to do is evaluate this integral here. So since we're just doing partial work towards our answer, let's try to do this calculation in a box just to keep everything organized. And then at the end we can come back and write our final answer down. Okay, in order to evaluate this integral, we're going to do a substitution. So this is good practice with some of our previous methods of integration. The correct thing to do here would be to sub u equal the denominator, and we're going to see that we'll get a ln form for this integral. Du, excuse me, du would be 2x dx. And looking up at our integral, what else would we have to take care of? Well, we would need an x dx in there. We're going to get that just by dividing by 2. Our integral, this x over 1 plus x squared, integrated with respect to x, is going to give us 1/2 du over u. And when we integrate our du over u, we're getting ln absolute value of u plus a constant. So final thing we'd want to do is just go back to our original variable, 1/2 ln absolute value 1 plus x squared plus a constant. So remember that all the work we did in this box is just to calculate this integral here, and we still need to give our final answer to the problem. So I'm going to say the integral of arctan x with respect to x, which is what we're ultimately looking for, is equal to x arctan x minus the value of this integral that we just calculated. So minus 1/2 ln absolute value 1 plus x squared plus a constant. So just a note about the algebra here, in case you're worried about the sign on the c. You know, if you had plugged literally into this expression and you had subtracted off both of these terms, then you would have had minus 1/2 times the ln term minus c. But remember that c is a symbol representing any real number. It's not necessary to write minus c here. Just writing plus c is much more natural, more conventional. All right, so that's our final answer there. We've had some great practice with seeing how the formal method works for integration by parts. And we got some additional practice as well because we got to do this little substitution. So many of these formal method problems will involve substitution. Not all of them, but most of them will. So it's good to be super comfortable with that substitution process before going into the integration by parts problems. Thanks for watching, and we'll see you in the next video.